or just of use for researchers. So today we have Robert Krasny from the Department of Mathematics. Real quickly before he starts talking, if you haven't signed in, please do so. And just to let everyone know, the seminar series is going to run through the month of May before breaking for the summer. So with that, I'll let Robert take it away.
Thank you, Marcy, and good afternoon, everyone. Thank you for coming, and thank you for the opportunity to present my work here. And so I'm going to tell you about this Treecode-Accelerated boundary integral Poisson-Boltzmann solver for electrostatics of solvated proteins. I'll be breaking down what that means. My collaborators, these are former postdocs here. Wei-Hua Gang is the one who did the Poisson-Boltzmann solver. Page and Lee, Hans Johnston worked out the Treecode algorithm. I'll tell you a little bit about that. And so let me tell you about the outline. The problem that I'm addressing here is the electrostatics of solvated proteins. In particular, we're going to be concerned with the electrostatic potential. And that's the first step along the way to eventually doing electrostatic forces. But this work is concerned with the electrostatic potential around a solvated protein. We're going to use the Poisson-Boltzmann implicit solvent model. Now, there's a lot of debate about the proper solvent model, and I'm not entering into that. Our goal here is to provide a more accurate and efficient Poisson-Boltzmann solvent. That's what we're going to do. And it's possible some of the techniques we use can be used in other contexts as well. I'm going to do a boundary integral formulation. I'll explain about that. And then to accelerate the numerical solution, we use a Treecode algorithm. This is used to compute long-range interactions accurately and efficiently. And I'll be presenting numerical results. So let me begin with the physical model. And I'll encourage questions at any point, please. The physical model, so imagine we have a protein, so it consists of a sequence of atomic charges. So here's a schematic of these atomic partial charges. And each of these atoms has a van der Waals radius. That's going to exclude the solvent molecules. You can imagine this is going on in 3D. This is just a 2D schematic. And then surrounding the protein are water molecules. So those are indicated here. 1, 2, 3. Of course, there are many, many all around. Okay, but they're excluded from this region here by the van der Waals repulsion of the atoms. So just imagine all of these spheres. Imagine this sphere rolling along the van der Waals surface. That's going to create a molecular surface. That's this dark line that you see here. So that's the envelope of a rolling sphere. The sphere represents a solvent molecule. Okay, in this molecular surface, it's also called the solvent-excluded surface. So this separates the cavity, the protein cavity in here, from the solvent domain outside. And then finally, in the solvent, we can assume that there are mobile ions, dissolved salt. So then these are the elements that go into the physical model. And I can say a few more words that in this model, we assume that the protein domain has these atomic charges, but it's also a dielectric continuum. It has a low dielectric constant. The solvent domain has no charges. It's got these mobile charges. I'll explain how those are accounted for. But the solvent domain is a dielectric continuum as well. And the dielectric is constant. There's a jump in the dielectric constant. There's a high dielectric constant representing the solvent. And now the goal here is to compute the electrostatic potential of this system. And in particular, we're going to be computing it on this surface, this molecular surface. And as well as the electrostatic potential, phi of x, we're going to be computing the electrostatic salvation energy of the system. So that's what we want to compute as a function of the input atomic charges, the dielectric constants, and the ionic concentration in solvent. And of course, this is one particular model. There's quite a bit of, I would say, debate about what the proper model for this interface region should be. But this is an implicit solvent model, which has the advantages of efficiency in comparison with explicit solvent. So the mathematical model here is as follows. So we've got a domain, let's call it omega 1, that's the protein domain. We've got the atomic charges. And the solvent domain is omega 2, and the boundary, the molecular surface, we'll call that gamma. So in the protein cavity, we've got this equation, the Poisson equation. So phi is the electrostatic potential, epsilon 1 is the dielectric constant inside here. These are the positions of the atomic charges, and these are the partial charges. So this is a Poisson equation in the interior, and then in the exterior, that's the solvent domain. We've got this equation. This is a linearized Poisson-Boltzmann equation. So there's a Boltzmann distribution of charge, which depends on the electrostatic potential. It's been linearized, so we just have phi of x over here. And the kappa bar here represents, that's the ionic concentration. If there are no mobile ions, this would be 0, then you'd have a Poisson equation outside as well. With this term here, it's a Poisson-Boltzmann equation. And then we've got the, on the molecular surface, gamma over here, the electrostatic potential should be continuous as you approach the surface from either side. That's phi1 equals phi2. And then the electric displacement, that's the dielectric constant times the normal derivative of the potential. That quantity should be continuous at the interface over here.
So you got the ability to do the nonlinear PB
Well,
choose different molecular surfaces?
You solve nonlinear problems by iterating linear problems. So a nonlinear solver, in principle, can be built on a linear solver like this. We haven't done nonlinear simulations ourselves yet, but that's one of the things we want to do.
On the solvent model, or the surface model, have you got different surface definitions as well?
Different surface. Well, we're using the molecular surface, and if you prefer to use a different surface, I'm sure the method can handle it. I'll explain more about the molecular surface coming up real soon. And there's a far-field boundary condition, so the potential should vanish at spatial infinity. So this is the mathematical description, and we want to. I want to say a few words about the molecular surface. So I'll do this in the context of an example. We took a protein 1A63. Oops, sorry, I pressed the wrong button. Oh, that gives away a lot, but anyway. So this is the RNA binding domain of E. coli rho factor. And it has 130 residues and 2,069 atoms. And so here's a picture of it I got from the web. And it's got these 3 helices over here. And then it has another domain that they call this a beta barrel domain. And so they believe that the binding takes place in this RNA binding is concentrated here. So this gives you some kind of concept of this protein. The molecular surface that we use in our numerical method, we use a triangulation of the molecular surface. This is created by some software called MSMS by Michael Sana and his collaborators. And so that software takes the input atom positions, and it produces a triangulation. And you can specify the density of triangles per unit surface area, and specifying density 1 for this protein, you get 20,000 triangles. And then if you specify density 5, you get 70,000 triangles. You get a smoother, more precise definition of the molecular surface. So we take this as input to our numerical method, okay? And so this separates the protein cavity from the solvent domain, as we've seen. And again, I'm certainly aware that there are there's not only different definitions of what the interface can be, there's even different software implementations of how to compute that interface. That's a separate question. We're using this one, which is widely used in this business. So,
you investigated how that surface definition affects.
have not done a lot of that. Have not done a lot of that.
Is this guy in Florida, Joe?
Yes. I know his name in a couple of his papers.
Yeah, and he talks about the importance of your surface definition if you want to calculate forces with it.
Yeah, I believe. Yeah. There's. I would say there are competing ways to define the surface, and that's again one of a long list of things that we should be looking into. So, but we invite collaborators to help us do that. So, let's continue with this example. So I'm going to show you some of the output before explaining how the method works. So, so this is an example of a computed surface potential using our boundary integral solver. And this is the Poisson-Boltzmann electrostatic potential. That's where the kappa is not equal to 0. And so what you get the ability to plot the potential at each triangle, essentially. On each triangle, we have a value of the electrostatic potential. It goes from negative values to positive values. And one of the things you can do, you can turn off the mobile ions. So turn that back into a Poisson equation and solve that. You get this picture here. At first glance, they don't look very different, but in fact, the colors are a little brighter here. So that's the screening effect due to the mobile ions that diminishes the electrostatic potential. And you can accentuate that by taking the difference, subtracting these two, and then looking on a different scale. Okay, you can see that that this region here is much more positive as a result of the mobile ions being present. Hey, no problem. Bye. So. So these are the kind of plots that the biochemists are interested in, and we became aware of this problem, I should say, over in the math department, and thought that we could contribute by trying to do it accurately and efficiently. So biochemists want to obtain these pictures in a short amount of time to do the kind of parameter studies. If you vary the position of an atom, or you vary the charge on the atom, or on a particular residue, you want to see what effect that has on the electrostatic potential as one element in a process of understanding the structure and the function of the protein. So let me move on now to talking about numerical methods, the Poisson-Boltzmann solvers. So these are grid-based methods, mostly finite difference, but also finite element methods. So in a grid-based method, one takes a box, puts it around the protein, and discretizes the space with a three-dimensional grid, either a Cartesian grid, or in the case of finite elements, could be a tetrahedral grid. And then one discretizes the derivatives, winds up with a linear system, which is typically sparse, and often the multigrid method is used to solve the sparse linear system. So these are some of the well-known software tools, the Poisson-Boltzmann solvers that are out there, which are heavily used. And these codes all provide good answers, but there still is a need to improve the accuracy and the efficiency, always. And recently, I would say, some of the work that's appeared in the context of finite difference solvers, higher order treatment of interface conditions. This is my former postdoc, Wei Gang, and he was a student at MSU with Guo Wei. They worked on that. And then also adaptive grid finite difference method has been developed. Alexander Boschitz and Marsha Fenman have been developing that. As an alternative, one can consider, so there are still some disadvantages with using a three-dimensional grid. And so one has to truncate the domain instead of satisfying the condition at infinity. Also, the definition of the molecular surface is difficult to achieve accurately with a three-dimensional grid. So
even the simplest sampling rate, which would vary. Stuff like that.
So, the alternative are these boundary integral methods. And so in these methods, one is able to reformulate the problem so you have an integral equation just on the molecular surface itself. It has some advantages and has some disadvantages as well. But I believe we've been able to make progress in overcoming the disadvantages. So some of the prior work, and I don't want to go into the full list of all the work, there's quite a bit of work. I would say, though, that the boundary integral methods are still not at the same level of development as these Poisson-Boltzmann solvers. These are in wide use all the time. These have not yet reached that point of being adopted by many people. We hope to change that. So what's needed first was to have a well-posed formulation of these integral equations. And this paper achieved that. And, but still, there were difficulties with the boundary integral formulation. I'll explain those difficulties as we go into the details a little bit more. But there's been quite a bit of work using the fast multipole method to accelerate the solution of the linear system that you get when you do this formulation. These are some of the people working in the area of the fast multipole method. We don't use the fast multipole method. We use the Treecode algorithm, which is an alternative. It's in the same general class of algorithms as the fast multipole method, but it really is an alternative to the fast multipole method, and I'll say a little bit more about that. Get up to it. So I'm going to go into more detail now about the boundary integral formulation. And so here we go. We've got these Green's functions. So this is the Coulomb potential. X and Y are points in 3D. So this is the well-known Coulomb potential. Point charge. This is the potential at X due to a point charge located at Y. And this is now the screen Coulomb potential. It has this exponential decay. Kappa is now defined this way here. This is, so from a technical point of view, the G0 is the Green's function for the Laplace equation in 3D. This G kappa is the Green's function for the linear Poisson-Boltzmann equation in 3D. And at any point in the protein cavity, remember, it's a Poisson equation in there. So any point, the electrostatic potential can be written this way here. So this is called Green's formula. Yeah. And the potential is, you've got a single layer over here, and you have a double layer over here. And you've got the source terms coming from the atomic charges. And in the solvent domain, you have another Green's formula. So this involves G0 here. This formula involves G kappa. There are no source terms. The mobile ion, the effect of the mobile ions is captured in this G kappa over here again, but it's a single layer plus a double layer over here. Now what's not known, these are integrals over the molecular surface.
Right.
Yeah. What's not known here is the value of the potential on the surface and the value of the normal derivative. But when you impose the interface boundary conditions using these formulas over here, then you get a set of integral equations. Now, there are various ways to do that. Here's the boundary integral formulation. I'm showing you the formulation that these people derive. So this is not the first integral equation that one would write down. One writes down the simplest integral equation, turns out to be ill conditioned. That was discovered. These people overcame that with this formulation here. So we've got now this parameter epsilon is the ratio of the two dielectric constants. And now this X is on the molecular surface. Okay? And you have these two coupled integral equations. Here's the electrostatic potential, here's its normal derivative. And that's for points on the surface. We've got the same quantities here and here. We've got these kernels, K1, K2, K3, K4. The source terms are over here. I'll go through and explain these kernels and source terms a bit. So the kernels are here. Now the K1 is just the difference between these G0 and G kappa. K2 and K3 involve first derivatives, and K4 involves second derivatives. Now, if you remember, the G0 has a singularity when x equals y. Okay? But this one has the same kind of singularity. Subtracting weakens the singularity. So K1 has a weaker singularity than either G0 or G kappa. Now that's critical over here, okay? Because if you do this naively, you're going to be dealing with either this term or this term by itself. And then you've got what are called hypersingular integrals, which are very tricky to deal with. And in any case, those methods turn out to be ill-conditioned on the discrete level. By doing this subtraction here, which was explained by these people, by doing this subtraction, you weaken the singularity. So this kernel over here, in fact, is a principal value integral, which is 1 degree less singular than a hypersingular. It's more tractable numerically. You have two coupled equations means that the system is a little bigger than if you were just dealing with one equation, but it turns out to be well conditioned when you discretize it. That has consequences for how efficient the solution can be performed. The source terms are here. These are the atomic positions. These are the charges, G0 here, and the normal derivative of G0, giving these source terms. We're going to discretize these equations. No questions?
This is kind of assuming that the surface is just kind of constant, huh? I
Did
mean,
you see the pictures of the surface?
Yeah.
I'm not sure. Maybe
I didn't.
let me just take a quick look back.
So forgive me.
This is
I was out of
but
town.
here's we're going to be solving on
Yeah.
triangulations like this. And
Right.
It comes from MSMS. And we're going to look at it as
I
a
was just
density.
thinking these are about some kind of average. I mean, this is just, this, so I was just wondering because the thing's changing all the time. And the epsilon would be changing. All this.
We take the structure from the protein data bank,
Yeah.
crystallized or NMR structure. We assume that's given. And we're simply solving the static problem. This is one step. Dynamics is going to come later. There'll be no dynamics in this talk. We want
Right.
to solve this problem.
And this is different than what Fred Richards did years ago. I mean, this is going back.
I think this stems directly from the paper by Richards.
Yeah, okay.
So that's the surface.
Yeah, all right. I remember. He
Yeah,
was a
so
neat
that's the
guy.
surface
Right.
definition. The question, the dynamics of the traditional finite element method, finite difference methods, they're way too slow to do dynamics with electrostatics.
That's right, exactly right.
So where you're really going to contribute is making that a lot more efficient.
I hope we can do dynamics more efficiently.
Okay, yeah, thank you.
But that's not part of this work.
Right, that's not what you're talking about now.
So we come back to these integral equations, and so the here's the formula for the salvation energy. If once you've solved for the phi and phi the n, then this expression here is the boundary integral formula for the electrostatic salvation energy. So this is what we're going to evaluate.
Okay.
So the discretization now, the principle here is to start with the simplest method. So we came across this principle after trying some more, let's say, complicated methods. So the simplest method is called centroid collocation. And that simply means that you have a discretization point at the center of each triangle, and you assume that the quantity you're integrating, either the potential or its normal derivative, is constant in each triangle. It's like the midpoint rule. If you evaluate an integral of x dx from a to b using the midpoint rule, this is the analog for a triangulation. The singular term we omit. Okay, so xi, these are the centroids of the triangles. Ai is the area of each triangle. And here are the integral equations again. You can see that, but now this is evaluated at the centroid of the ith triangle. And the integral is replaced by a sum. J not equal to I means we have omitted the singular term. Okay, so this truly is the simplest discretization we can think of. Of course, there's a lot of work on evaluating these integrals with higher order accuracy. Those methods tend to be more complicated. The final goal is to get the best performance. So we don't mind using a lower order discretization method like this if we can recoup the efficiency with the methods we use to solve this system. So this is a linear system. Let's say schematically, it looks like AX equals B. The matrix elements here are all these factors that you see here. And the X, the unknown vector here, is the electrostatic potential and its normal derivatives. The right-hand side comes from the source terms over here. So the linear system has no special properties. It's a dense linear system. We solve it by this algorithm called GMRes. And so GMRes algorithm requires a matrix vector product at each step. It's an iterative method. You iterate until the solution converges to some tolerance. At each step, you're taking this matrix, whose elements you see here, and multiplying by a current iterate of the potential and its normal derivative. Okay, and that's expensive. Okay, the expense of computing these sums was one of the drawbacks to using boundary integral methods. And so it requires some kind of fast summation algorithm. That's what I'll tell you about. The fast summation, here's just let's abstract this as an example of the kind of sum that needs to be evaluated. If G kappa is the screen Coulomb potential, and xi is some point, this would be like an electrostatic potential at xi due to a set of charges. So the options for evaluating these sums, you can write a loop over I and a loop over J. That's direct summation. And that's like doing particle-particle. If we think of these centroids as particles, that particle-particle sum here would be an order n squared operation count. And that's been a hindrance to using large values of n, which of course you want to do in order to get the details of the molecular surface. As an alternative, there's a Treecode algorithm. And what the Treecode algorithm does, it performs particle cluster interactions. A particle interacts with a whole cluster of other particles. And this was first done by Barnes and Hutt in the context of gravitational simulations with interacting point masses. That's the case when kappa equals 0. And it reduces the operation count to n log n. So you're making an approximation, but you're getting greater efficiency. And with some former postdocs, we worked out a Treecode algorithm for the case kappa greater than 0, this kernel over here. So we're going to use that. Another alternative is the fast multipole method, which goes a step further, and it performs cluster-cluster interactions. And in principle, it achieves an operation count of order n. This was first done by Gringard and Rocklin for the Laplace equation. For the screen Coulomb potential was done by Masha Fenley and her collaborators. And, Leslie Gringard, Jinfeng Wang also had a paper applying the fast multipole method to this kernel here. But you pay a price because this algorithm is more complicated than the Treecode.
Oh.
Now, the Treecode is more complicated than direct summation. So this is kind of a compromise over here. We like this algorithm, and we're promoting this Treecode, trying to develop it, push it as far as we can. I'll tell you a little bit about how this Treecode works, but I won't dwell on too many details. So the idea of the Treecode is this. Suppose your particles, of course this is not a molecular surface, just imagine a scattered set of particles. You want to compute the electrostatic potential at each particle due to all the others. So there's a hierarchy of clusters, you see over here. And so this particle, if it wants to interact with all of these by a particle cluster interaction, really can't, okay, because there's no separation. This particle can interact with all the particles in this cluster because the particle is separated. Okay, what about these? Well, the particle can interact with these clusters. The particle here can interact with well-separated clusters at this level. You get to a point at which you've accounted for all the far-field interactions, and then you do direct summation locally. The formula looks like this. If you needed to evaluate a sum, j goes from 1 to n, okay, you break it up into a sum over clusters. So there's a given xi, for example, this particle. It's not going to interact one by one. It's going to interact by choosing a set of clusters. So this particle might choose this cluster, then these two here, and these two here, etc. Come up with a sequence of clusters. And then this is the interaction between a particle xi and all the clusters, all the particles in a cluster C. And the options for doing this particle cluster interaction, you can do it by direct sum. If there are very few particles here, that's the right thing to do. Or you can use a far field approximation. And so the far field approximation is in essence a multipole approximation. It's the same multipole approximation you would learn about in an E&M class. Although it can be expressed in different coordinates, we use Cartesian coordinates for simplicity. If neither of these options is appealing, you can descend to the children. Okay, so for example, I said you can evaluate the interaction between this particle and this cluster here, but if this cluster is not well separated sufficiently, you might want to do the interaction with just these clusters out here. So you see that there's a tremendous amount of, let's say, adaptivity available in this algorithm for evaluating these sums. In a nutshell, that's the Treecode algorithm. So I'm skipping a lot of the details here. If you wish to ask, yes, go ahead.
So when you separate the particles here, is it always evenly separated, or you can have a kind of weighted way to separate certain
Yes, I'll show you some kind of weighted way in a moment. I'm going to show you this picture here. So for example, remember this was our schematic of a molecular surface. And so many algorithms, including the fast multipole method, use uniform clusters on each level. And the uniformity gives you some advantage, but at the same time, you see that there's a lot of empty space in these clusters. So what we do is we use clusters that are adapted to the molecular surface. So all we do is we shrink these clusters around the particles they contain. You get a more accurate representation of the molecular surface, and this pays off when the algorithm is run. So whatever criterion you use to determine whether a particle and a cluster are well separated, that criterion can be satisfied at higher levels in the tree. You gain efficiency in the algorithm without losing accuracy, hardly, using these kinds of adapted clusters. So this is kind of a weighting, but there's other ways to consider weighting. When one considers parallelization, there's a whole other issue there of load balancing. So I'm not sure if I've answered your question enough, but okay. So we'll move on to some results. So I apologize for all the dense numbers over here, but I'll try to lead you through. We did a comparison. TABI is our Treecode-Accelerated boundary integral solver, and APBS is the adaptive Poisson-Boltzmann solver. Nathan Baker, Michael Holst, others have developed. We took this as one of the standard PB solvers that are used. And I'm going to show you the top half of this table is the boundary integral results. The bottom half are the APBS results. So for the boundary integral results, we took a sequence of densities going from 1 to 40, 20,000 triangles up to 500,000 triangles. And we computed so we did the GM-res, etc., computed the electrostatic salvation energy. Now, the DS stands for the discretization. This is obtained using direct sum. There's no Treecode used in obtaining these values. So we did the O of n squared operation count to get these values. These are the Treecode values of the electrostatic salvation energy. The error is in these two tables. So this table here is an estimate of the discretization error in the boundary element solution of the integral equation. So we extrapolated these values to get our estimate of the exact electrostatic salvation energy. That's this number over here. And then we use that to get these estimates of the error. So as you refine this triangulation, the error is going down. So these values are converging to this value over here. And this is now the error that's induced by using the tree code instead of the direct summation over here. So we wanted to have it such that the tree code approximation error is less than the inherent discretization error in the boundary integral method. Here. We've achieved that. So I haven't told you about the parameters that go into the tree code. There's an order of the multipole expansion that's used. There's also a criterion for determining whether particles and clusters are well separated. So as in any algorithm, one has to decide on some numerical parameters, but it's not too hard to decide on those parameters and get these results. Now, you want to see the CPU time. So the O of n squared direct sum, of course, increases prohibitively. The tree code CPU time is much less than the direct sum time here. This is the number of iterations in GMRes. It's very modest in this case due to the well-conditioned integral equations we're using. This is the memory usage in megabytes for the direct sum and for the tree code. Now, comparing with APBS, we put a box around the protein, and we choose some grid size. So the protein is longer in one direction than the other two. And this is the maximum grid spacing. And these are now the computed electrostatic potentials. These values are also converging. We extrapolated these values to this value here. And we use this now to estimate the errors in the APBS salvation energy. CPU times are over here. Memory usage is over here. So I'm highlighting this line and the blue line here because in both cases, the error is about 1.2 or 1.3%.
Oh.
And you can see that the boundary integral simulation is faster than the grid-based simulation, and it uses a lot less memory.
I guess typically folks would use 0.5 Armstrong.
This one.
H max, yeah.
The error would be, according to this, 5% error, which may or may not be, may be okay in some cases, or may not.
Well, even the one might be okay.
That's true. This was an accident that this happened to be so
Why is
small. This number is fortuitously close to the final result.
Oh.
But this is outside the domain of convergence of this. You wouldn't want to rely on that using 1.63 angstroms.
Oh.
There's no way of predicting this in advance when you get lucky.
One of the big advantages of APBS is the large system size you can do and break it down and so also cores out there.
We'll show you some parallel results here. So, but I'm going to present this table pictorially here. So here's a same comparison. These are just giving more details. So in the boundary integral, the density went from 1 to 40. This is the number of triangles. These are the parameters in the tree code. We'll talk about that offline if you wish. The APBS grid spacing went from this to this. And first, so here, this is now the CPU time versus the error for both methods. And now this has both the Poisson-Boltzmann as well as Poisson results in it. So the boundary integral results are these black lines. You see the Poisson, so as the error decreases, the CPU time goes up in all cases. The boundary integral method solves the Poisson equation faster than the Poisson-Boltzmann equation. So the dashed line here is lower than the solid line here. The grid-based APBS results are here. Okay, so the crossover here is around about 3% error. APBS is faster if the error is greater than 3%. The boundary integral method is faster if the error is less than 3%. For this particular case, for this particular implementation, both algorithms are capable of improvements. And there are even ways to improve APBS. The treatment of the boundary condition there can be improved using a tree code algorithm, which I hope will be at least tested at some point. And for the Poisson equation, the crossover is around 6%. The memory usage is like this. So memory as a function of error. And so you can see that the boundary integral method is it's using more memory, but the memory usage increases at a more moderate rate than for the grid-based method.
So do you have an idea of where that area really becomes significant for the kind of things that people, beyond just looking at electrostatic potentials and surfaces, but doing quantitative calculations to PD, where does the area really impact those things?
You guys are going to tell me what error do you need?
Well, we would be happy with 5% error, right?
Well, you'd be happy with it because that's
what you get.
that's all you can get. But would you be? How much happier would you be with 1%? So of course, it needs to be studied. How
So that's what I'm asking.
that has to be done in collaboration with you guys, because we're trying to learn now about the biological applications, for example, pKa computations, which could be sensitive to small errors in electrostatic potential. And if it matters there, then you want to pay the price. Yeah. So I am parallel performance. So this algorithm. So we chose a particular system here with it's the same protein, but it's got 130,000 triangles, some tree code parameter values. This is a case where the error in the electrostatic potential and its electrostatic salvation is 1.3%. And because we're using so little memory, relatively speaking, we can use a replicated data algorithm. So the entire discrete system is copied over on each processor. But each processor is only responsible for computing the sum due to a segment of the triangles. So it's the simplest. It's the simplest parallel implementation that's possible. We did it in MPI, and these are still pretty modest results because we only used up to 8 processors, and we did achieve good speed up. We had parallel efficiency of 80%. Again, it's a relatively small problem. So we're getting ready to do larger problems and see what we achieved there. This was for the Poisson-Boltzmann equation. Remember, the Poisson equation is solved more efficiently. We get solved using 8 processes. 50 seconds, still 80% parallel efficiency. Now that's not fast enough yet to do good dynamics, but with a system of this relatively small size, one is eventually, well, actually pretty quickly, going to run into saturation. And so we were able to implement this parallelization pretty quickly. It's not terribly complicated. And again, that's because we use this replicated data approach, and that's because we're using small enough memory so that each processor can hold the entire system in it. Of course, some kind of distributed memory is going to be required if you get to really much larger systems. But we can go quite a bit up in terms of the system sizes before we have to use a distributed memory approach. So I'm ready to talk about the summary here. This is the Treecode-Accelerated boundary integral PB solver. So the CPU time here, this comes from the Treecode. Order n squared is reduced to n log n. Do larger systems as a result. The advantages of this, it's relatively simple to implement in serial and parallel. So relatively simple, in particular, in comparison to the fast multipole method. It has efficient memory usage. It's geometrically adaptable. So that's important, I believe. We're hoping to tie this out on things like membranes, possibly other structures, DNA as well. And so the code is available at SourceForge. And the references for this work, so the Treecode was developed in this paper. This is the Journal of Computational Physics. And with Weiwa, we published these results I presented today, also in the JCP last year. And the current and future work, well, there are numerous places in which the code can be improved. We have to investigate those and see if they really lead to better performance, higher order quadrature schemes, things like that. the treatment of the molecular surface, possibly. And we have our eye on computing forces, so we're reading papers, learning about how to do that in the context of a boundary integral formulation. We're interested in biomolecular applications. We're also learning about how to do pKa computations, so we understand the importance of that for determining the active sites of these proteins. So we're interested in collaboration with people in biology, biochemistry. So if you'd like to talk to me about that, I'd be happy to chat with you. So thank you very much.
So do you think it's the electrostatic component that's really a limiting factor in pKa computation accuracy at the minute? Or?
I don't know. There are other components there, and it's just one component. We're really beginning to learn how to do those. And I missed the opportunity to study enough chemistry. Faculty. I'm trying to make up for that.
That's an important problem.
Yeah.
So, and have you talked to Nathan Baker and APBS folks about that?
Yeah, in fact,
But that could be a really
Weiwa went to visit the Pacific Northwest lab last summer, and the plan is to implement this TABI as an option in APBS. And I hope they're doing that. I think it's going to come out, it's supposed to come out in the next version of APBS. That's what Weiwa told me.
Any other questions?
So how fast do you need to be for in this MD simulations
MD,
with PD?
how fast do you want? I mean, we didn't, so we would have to run AMBER, MD simulation, and then see if we, say using APBS over there, and then compared with TABI, we haven't done it yet. But I would say that we're still far from having a code that computes forces in this Poisson-Boltzmann context. We're still beginning to do that. And I don't know how long that's going to take us to do that. But that's one of the obvious next steps.
There's a chap called Robert Krasny, and he's implemented IAPBS as kind of an interface for holding in lots of different EV calculations with AMBER and charm.
I haven't heard about that.
Okay.
Might be a
IAPBS.
shortcut some of the run code.
That sounds
Getting
good.
your forces. IAPBS. Small I.
I'll look that up.
Nice.
Okay, well, thanks. It's good to have you here.
Likewise.
Sorry I missed you. Yeah, I just got back from Boston.
Thanks for coming.
Yeah, glad to be here.